Good afternoon, dear students. How are you, my dear students? I hope you all fine, and I am fine. Today's class, we will discuss the topic uses of hydrogen peroxide, structure of hydrogen peroxide, and hydrides and hydrogen bond. Okay. So, in the previous class, we discussed about heavy water and hydrogen peroxide physical and chemical properties and the synthesis of hydrogen peroxide. In this class, we will start from uses of hydrogen peroxide. So, hydrogen peroxide is one of the important compound for our daily life. Because of the oxidation ability of this hydrogen peroxide and the harmless nature of the disproportionating compounds H2O and oxygen. Okay. Disproportionating as H2O and oxygen. So, product or the disproportionation of this hydrogen peroxide produce the harmless product like water and oxygen. So, it is harmless and we can use this for many applications. Hydrogen peroxide is using here to treat the water or oxidizing the water. So, you can write here oxidize pollutant in water. So, hydrogen peroxide used here to oxidize the pollutant which is present in the water and use this as an mild antiseptic. And also uses bleach in textile industries. Textile industries, paper industry, and hair care product. In also using in the hair care product. And one of the most use of this hydrogen peroxide to retaining the original color of the painting. Hydrogen sulfide which is present in the air is reacting with the white pigment. It's also in the white pigment in the old painting. Okay, so it convert this white pigment is into the black color. So it is lead to forming the lead sulfate solution. Okay, so the compound hydrogen sulfide in air is reacting with white pigment is present in old paintings. It's turned that white color into the black color. That means the compound is converted into lead sulfide. Okay, lead sulfide. Now, hydrogen peroxide is the it is using here to restore that white color. How? The hydrogen peroxide is oxidizing that black color. It is an oxidizing agent. We know that it is also the oxidizing and reducing agent. Here hydrogen peroxide is oxidize that black color. That means the lead sulfide into the white color. That the lead sulfide is converting into lead sulfate by treating this lead sulfide with the hydrogen peroxide to converting this lead sulfate. So, it can easily restore that white color of the old painting. So, white color of that old painting formula Bb3OH twice, CO3 twice. Okay, so this is reacting with hydrogen sulfide, which is present in the air, in the atmospheric air. Now this reaction between this white color and hydrogen sulfide, both are combined and they become black color. They produce black color. Now this become lead sulfide. Okay, and the product or the black color is lead sulfide. So we treat this lead sulfide with the hydrogen peroxide to restore this white color again in this old paintings. Treating this lead sulfide with hydrogen peroxide, it produces lead sulfate, BbSO4, lead sulfate, and 4H2O. This is one of the important use of this hydrogen peroxide. Next is structure of hydrogen peroxide. So it can exist in the gaseous base and also in the liquid base. Now this molecule is adopting the gaseous phase and also in the liquid phase in skew conformation. So in gas form and also in the liquid form, it adopts skew conformation. Why it adopts the skew conformation? Because of this interaction of OH bond. So skew conformation means it will show the structure skew formation. This is oxygen. This is also oxygen. Now this first oxygen is connected with one hydrogen. Okay, this is hydrogen, this is oxygen, this is also oxygen, and this oxygen is connected with another hydrogen. This is skew conformation of this hydrogen peroxide, H2O2, H2 and O2. See this one, this OH, 2 hydroxyl group is present in this hydrogen peroxide compound. This is one hydroxyl group. What is hydroxyl group? OH, another OH. So we have 2 hydroxyl group, OH, OH. Okay, they are in skew conformation. Now this OH, first OH and second OH have some repulsive interaction in this OH bond. Okay, so there we have some lone pair with a lone pair of electron in the each oxygen atom. We have lone pair of electrons. Lone pair of electron, we indicate this 2 dot. That means 2 electrons. Oxygen contain 2 lone pair, each oxygen contain one lone pair of electrons. So because of the presence of this lone pair of electron and the presence of OH group in the OH bond in this hydrogen peroxide, their repulsive interaction is going on in this hydrogen peroxide. Because of this repulsive interaction of one hydroxyl group with the another hydroxyl group, it is showing that skew conformation in gaseous form and in the liquid form. H2O2 is a non-planar structure, a non-polar structure. Non-polar structure means it exists like this, OH, OH. So it's not showing any kind of electropositive or electronegative in the both the end of this compound. Okay, so both are same, so they are not showing the different symbol or the different edge of this compound. That's why we can say this hydrogen peroxide is a non-polar compound, and their molecular dimension in the gaseous phase and uh, solid base are showing in this figure. This is the molecular dimension structure for gaseous and solid base hydrogen peroxide. Now you can see this one, it's the structure is looking like partially opened book, and the angle between that two plane, it is explaining here, this is one plane and this is another plane. Okay, one plane and this is in another plane. Generally hydrogen peroxide it is existing in the skew form. It's not in the same plane, okay, but one hydroxyl group with the another oxygen molecule, they are in same plane, and one hydrogen which is joined with the oxygen, they are in another plane. Okay, they are in another plane, they are in opposite plane. Okay, so this is explaining here in the structure of partially opened book. See, this is the structure for gaseous form of hydrogen peroxide. This is the structure for solid form of hydrogen peroxide. So the angle between that two plane in this gaseous form is 115.5 degree. In here the angle between these two plane are 90.2 degree. 90.2 degree. For the structure, in that center of that two plane, oxygen is placed. Okay, so oxygen bond with another oxygen. Okay, it is placed like that, and the hydrogen which is connected with that oxygen, they are in this same plane, so it is exist here, and the hydrogen which is connecting with the first oxygen, it is not in this plane, it is in the first plane. Here it is exist. So the angle between this hydrogen, this two bond between this oxygen and hydrogen and oxygen bond is, it is 94.8 degree. 94.8 degree. Here you can see the same structure like the previous one in the gaseous phase hydrogen peroxide. Oxygen is placed in the center of that structure and connecting with hydrogen. First oxygen contain one hydrogen. It is in another plane. You can see this, the angle expand from here. Here it is 94 point, in the gaseous phase of hydrogen peroxide you have 94.8 degree, but in the solid base you have 101.9 degree. And the measurement here 0.95 angstrom, the bond length of that bond, and here it is 1.47 angstrom. Now it is differ in this gaseous phase from solid base from the gaseous phase. In this solid base you have 0.98 angstrom. In this bond 1.46 angstrom. This is the structural explanation of hydrogen peroxide. Next topic from this hydrogen unit is hydrides. So hydrides are with the form of hydrogen. Hydrogen is combined with the electropositive elements like metals and non-metals. They produce hydrides. Okay, so the combination of hydrogen with metals or non-metals. Metals or non-metals. They can produce the hydrides. And also it can form ternary hydrides with the two metals. Example, lithium aluminium hydride. Another example, lithium borohydride. Generally, hydrides are classified into three types. First type is ionic, second type covalent, third one metallic. First type is generally known as saline hydrides. Second type is molecular hydride. So the another name of covalent hydride is molecular hydride, and the metallic hydride is interstitial hydrides. So we have three types of classification in this hydrides. In this ionic hydride, hydrides are formed with the element in the combination of hydrogen. They are lower electronegative compounds than the hydrogen. Okay, so they can form only in the ionic one lower electronegativity. When the elements contain or it have higher electronegativity than the hydrogen, and they form the covalent hydride. So they have higher electronegativity. The element which is combined with the hydrogen, that element have higher electronegative one, then that can form the covalent hydride. Then the element hydrogen is combined with the element which contain lower electronegativity, they can form only the ionic hydrides. So the first type, ionic hydride or saline hydrides, are composed with the electropositive compounds like the electropositive compounds, mainly the electropositive compound in our modern periodic table, they are alkali metals and alkaline earth metals. But here we have some except case in this alkali and alkaline earth metals, beryllium and magnesium. Both are except case in the ionic form. They can't form the ionic compounds with the combination of hydrogens. Here the formation of ionic hydride mainly by the transformation of electron from metal to hydrogen atom. So the hydrogen atom is behaving here as an acceptor from the acceptor of electron from the reacting metals or reacting active metals or reacting electropositive metals like alkali and alkaline earth metals. They can form the compound in this reaction about 400 degrees Celsius. So that can form this 400 degrees Celsius in the reaction condition. Generally they are salt like compound, high melting, they have the physical properties like salt like structure and high melting point. White crystalline solids like hydride can form with the combination of metal cations like alkali and alkaline earth metals with the hydrides. For example of the formation of hydride, 2 lithium combined with 1 molecule of hydrogen, they produce 2 lithium hydride. So this is the formation of hydride. And second one example, calcium, 2 moles of calcium is combined with 1 molecule of hydrogen, they produce 2CaH. H2. Second type of hydride is covalent hydride or molecular hydride. Here the bond formation only because of sharing of electron between the compound, between the element which is combined with the hydrogen. So the mutual sharing of electron in this reaction is produced here covalent bonded hydride or the molecular hydride. Sharing of electrons. So the common example for this covalent hydrides of non-metal is methane, ammonia, water, and hydrogen chloride, that means hydrochloric acid. This covalent hydride further classifying into three types. First type is electron precise. Second type electron deficient. Electron deficient, and third type is electron rich compound. So the example for this electron precise compound: methane, ethane, silica hydride, etc., germanium hydride. And the example for the electron deficient compound: B2H6. And for electron rich compound: ammonia and water. These are the compound electron rich compounds. Most of the covalent hydrides are discrete compounds and small molecules. They have the relative weak intermolecular force. So they have relative intermolecular force. Relative intermolecular force. Because of the small molecules is existing the weak intermolecular force, that or the relative intermolecular force is generally, because of this force they are generally gaseous compounds or the volatile liquid compounds. Volatile liquids. Next case, the third type of hydride, metallic hydride or interstitial hydrides. It is obtained only because of the hydrogenation of metals. Hydrogenation of metals and alloys. Here in the process of hydrogenation of metals and alloys, the hydrogen is this hydrogen which is reacting with this metals and alloy, it is occupies only the interstitial site or the void of that metal. The space of the metal it is occupied. So that's because of this hydrogen place in the void or interstitial site, it's known as the metallic or the interstitial hydrides. In this metals, the metallic hydrides, their character are similar with, or their properties are similar with their parent metal, which is reacting with the hydrogen. So they are non-stoichiometric one, and they have variable compositions like titanium hydride. So So titanium hydride range, it is not under the stoichiometric. So it can vary from 1.5 to 1.8. And for the palladium hydride, this is also one hydride, metallic hydride or the void hydride or interstitial hydride. They have some range. It is not undergo the stoichiometric one, but it is in the non-stoichiometric composition. So the variation are in the palladium hydrides 0.6 to 0.8 range. They are light compounds. Metallic hydrides are light compounds. They are inexpensive compound. They are thermally unstable. Thermally unstable. So because of this characters like lightweight and inexpensive and the thermally unstable, we use this hydride, metallic hydride, to store the hydrogen. So this is one of the application of this metallic hydride. And in this metallic hydride also we have some exception case. In the electropositive metals or some other metals, electropositive metals and some other metals can form the stoichiometric compounds. Not given the range like this, but they can the definite compounds like MH and MH2, that means metal hydrogen, okay. So they can form the compound like this. For the metals, what are the metals is involving in the stoichiometry? Titanium, zirconium, hafnium, vanadium and zinc. Okay students, today's topic over. Up to this types of hydride. This is important question, type of hydrides, study well. Okay, thank you students.